Okay, so here's our new formula right here. And of course, now it's time to bust out the exponential decay formula, right? And this is, you can write these things down, right? But this is the original value, right? And the cool thing about this formula is that, technically speaking, that could be the number of undecayed nuclei, like as a pure number, right? But this can also be the number of grams you have. You can also throw activity in there as the original amount, because everything about that thing that's proportional to it, the number of nuclei, is going to decay with it, right? Okay. And of course, this is an inverse exponential, right? So it's one of these, like that asymptotically approaches zero and all this stuff, right? And where it comes from is this, right? The notion, here's the notion. We can set up a differential equation, and that is that the rate at which n changes with time, right, equals minus lambda times n, right? And this is activity, and then we know that it's lambda times n like this, right? So what we do is we guess that n equals n naught e to the minus lambda t, right? And then we can do a chain rule, right? If we take the derivative of this, right, we get, well, we just pull the minus lambda out in front, and we get n naught e to the minus lambda t, right? Okay, and then this is beautiful because that's just n, right? And we have this situation. The rate at which n changes is minus lambda times n. Same thing, right? The rate at which it changes is minus lambda times n. And if you're not in calculus right now, and you're not really good at calculus, that might have gone right over your head. That's okay. Just put it on the back burner there, right? Okay. And then here is another formula that they give you that's totally unnecessary, but if you want the activity, it's lambda n is lambda n times that, right? And I think there should be a minus sign on there, but that's okay. Okay. Then there's this notion of a half-life, right? And here's a relationship that's going to help you go between half-life and decay probability, right? But the half-life is literally the time for half the nuclei to decay, right? So in one half-life you have half left. In two half-lives you have a quarter of it left. In three you have 1/8. In four you have 1/16 of the original nuclei left, right? And you can get this way. We can derive this formula, right? Let's do this. Let's see. I know that a half n naught equals n naught e to the minus lambda times the half-life, right? This is the definition, right? So it is the time at which, using this formula, you get half the original, right? So now we can get rid of those guys, right? And we can rewrite this 1/2 equals e to the minus lambda t 1/2, right? And then I can rewrite it this way: 2 equals e to the positive lambda t 1/2, right? Because of, I don't know, there's some trick, right? There's some math trick. Okay, and now I can take the natural log of both sides, equals lambda, right? And then finally we can just recast it this way, right? Divide both sides by lambda. Okay, so that's where it comes from. And then finally, just the notion, if we make a graph of this, right? This is a graph of this, okay? These half-lives occur over and over, right? So in 20 seconds, right, you see that it's started at 100, got to 50, right? We expect then in another 20 seconds it will have divided in half again. This is, by the way, one way to see if a curve is an inverse exponential, right? Just check. Find the half-lives. They should all be the same. The next half-life should occur 20 seconds later, right? We should be at, instead of 25, 12 and a half, right? Indeed we are, right? So the half-life here is 20 seconds, okay? So let's do a problem. Now, some people might say that the answer to this problem is none of your business, okay? But, there it is, right? Okay, so what is the per second probability of a nuclei decaying? I'm going to need this a bunch of times, so I'm going to do this, right? So I'm going to use this formula here, right? So lambda is ln of 2 divided by the half-life, right? Okay, so that is ln of 2 divided by 128.4. Okay, ln of 2 divided by 128.4. And I get that it's 0.05, oh, I'm sorry, 0.005398.3, and I'm going to store that in A. Okay, and that's per second probability, right? Okay, and then it says if you start off with 32 grams, how much is left after 385.2 seconds? Okay, so let's do that. Okay, and I'm just going to use the grams as my number of atoms. I'm not going to calculate number of atoms because the answer should be in grams, right? We're going to get grams, right? Okay, so we're going to go 32 is my N naught, right? Okay, so N equals 32 grams is my original amount, e to the minus 0.005398.3 times 385.2, right? So let's try that. 32 times, where's my e to the whatever? Oh, there it is. E to the parentheses negative a times 385.2. And when I do that, it equals exactly 4. Like my calculator says 4, and then we could say 4.0 grams, right? Okay, so there's my first answer. I've got 4 grams. And then the question is, of course, why is it exactly 4 grams? That could be a question, right? And of course, the answer is that 385.2 divided by 128.4, right? This is an integer number of half-lives. Okay, whoops. I multiplied them, by the way. That's not an integer. Okay, that's exactly 3 half-lives, right? So you would expect there to be 1/8 of what you had left. Okay, so look for that on tests. They'll tend to give you integer multiples of half-lives, and even if it's not an integer multiple, right? You can do a lot of stuff on multiple choice tests, right? Say, okay, it's between 2 and 3 half-lives, so it's between 1/4 and 1/8 of the original amount, right? Okay, so now we want to do after what time is there 23 grams left? Well, that's a little tougher, okay? So let's erase that. Remember that our lambda is equal to, we calculated it, right? 0.005398.3 per second probability, right? Okay, so now we've got it. This one, I don't think, 23 is a prime number, right? So we're going to go, we're using n equals n naught e to the minus lambda t, right? So 23, dyslexics beware, equals 32 e to the minus lambda t, right? Okay, so now we want to solve for t, so what am I going to do? What I'm going to do is I'm going to do algebra here. Let's go n divided by n naught. Okay, that's right, and then I'm going to take the natural log of both sides. That gets rid of that, right? And then I'm going to divide by negative lambda, right? Yeah? So now we can just plug those numbers in, right? ln of 23, 32, divided by negative okay, so let's figure that out. Okay, natural log of 23 divided by 32 divided by negative alpha a. Remember, this will be a negative number because it's less than 1, and then we divide by a negative, it should be positive. And I get 61.17 seconds, which with 2 sig figs would be that, right? And then the final question is, what is the activity when there's 23 grams left? Well, let's see, we got to do the mass of it. Okay, when there's 23 grams left, what's the activity? I think I'm going to erase again, right? So my lambda is, remember, is 0.005398 per second, right? N is the number of moles times avocado's number, right? Okay, and then if there's 23 grams left, the moles is 23 divided by 210.987, okay? And then Avogadro's number is 6.02 times 10 to the 23rd, right? And then, of course, the activity is lambda n, right? So it's lambda times that, right? So I'm going to multiply this by lambda. Okay, so we're all set now. Okay, so let's see, 23 divided by 210.987 times 6.02 e to the 23rd times alpha a is where I put the lambda. Okay, and I get that this is 3.543 times 10 to the 20th decays per second, right? Which is, by the way, a decay per second is a becquerel, as in Antoine Henri Becquerel. Yay. All right, there you go. Happy exponentialing.